Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Today I want to talk about vector bundles and the notion of sections of a vector bundle. Now, this notion is something that geometers use to generalize the notion of vector-valued functions on some sort of geometric object. And the reason why we need such a generalization is that we'll use it in particular to alleviate the problem of paucity of functions in projective geometry. Okay, so let's have a look at this problem that we have, this problem of paucity of functions. And to really appreciate this problem and also the reason why we need to generalize the notion of functions, we need to have a little think again as to why we are interested in looking at scalar valued functions. Now, of course, this is something that's so ubiquitous in mathematics that it's easy to forget what we do with them, okay? So let's just suppose we start with R smooth functions, f1 up to fr, and they're smooth functions on x, so x here will be some smooth manifold. And let's suppose they're real valued. So what can you do with them? That's good, okay? So the first thing is that you can put them together in a tuple, okay? And then use it to map from our manifold x to Euclidean space R to the R, okay? So in this case, you have a map from here to here, and if this is large dimensional, if R is big enough, of course, you can make this an embedding, so you can capture all the information of x that way. So that's one thing that you can do with functions. Another thing that you can do with these scalar valued functions is you might be interested in looking at subsets of x, interesting subsets of x. And one way to get interesting subsets is to study common zeros of functions. So you can look at the set of common zeros of f1 up to fr. And that's called a subvariety of x, and that's something you can do with these scalar valued functions. Okay, so it looks like we like to have lots of scalar valued functions. Where does the paucity of functions occur? Okay, so let's change our settings slightly, and suppose we consider here the complex situation, where we want to look at holomorphic geometry. So for simplicity, let's consider a compact one-dimensional complex manifold, X. So in other words, just a compact Riemann surface. And the simplest example of that is the projective line over the complex numbers. So if you're not too familiar with this sort of object, let me just describe this simple example here. The way you should think about it is it's just a complex plane, and you compactify, making a one-point compactification by adding just a point at infinity. Okay, so if you want to study this, you want to study it using functions on this x, and the types of functions you're interested in are holomorphic functions. But what do we find in this case here? Well, Liouville's theorem tells you that, in fact, the only holomorphic functions, f from x to c, that you have are the constant functions. Okay, so why is that true? So let's look at this special case here of the projective line. The general case follows from the same reasoning. So in this case of the projective line, you have the complex plane compactified with a point at infinity. So what does it mean to have a holomorphic function on all of that? So firstly, you have a holomorphic function on all of the complex plane, but it also has to be holomorphic and in particular well-defined at infinity. So that tells you, in fact, it has a definite value at infinity, and in fact the function has to be bounded. And Liouville's theorem, as it's usually stated in the first complex analysis course, is that if you have a bounded entire function on the complex plane, then it has to be a constant. Okay, so you don't have many constants in this situation. Okay, so you just have the constants. So let's see what you can do with those constant functions in these two situations. Okay, so if this is f1 to fr, you're looking at just holomorphic functions. Each of these is constant. So when you have the map from x to, in this case, c to the r, you only get a constant map. So of course, with that constant map, there's no way you can get interesting information about this complex manifold x. Okay, so there's no uses for it here. Okay, what about studying common zeros? If the only holomorphic functions you have are constants, well, the constant could be 0, in which case the common zero is going to be all of x, or it could be a non-zero constant, in which case there are no zeros. So there are no interesting subvarieties of x if you look at holomorphic functions. So this is the problem of paucity of functions, which occurs typically in projective geometry, and also, as you can see, when you study compact complex manifolds. So the question now becomes, well, what can we do about that? Is there some sort of generalization of the notion of functions that allows us to, well, do what we did here? And the answer is yes. And what we need is firstly the notion of vector bundles, which I've described in a previous video, and also the notions of a section of a vector bundle. Okay, so let's do that. So remember, when you talk about vector bundles, you can do this in lots of different contexts, okay? And it depends on the geometric category. And the usual ones you look at are the geometric category where C is either the category of topological spaces, or the category of smooth manifolds, or the category of complex manifolds. There are also versions for algebraic varieties and also for schemes, but that's a little bit more complicated. So to be a vector bundle, of course, is the data of a morphism inside here from V to X. And of course, remember, each of the fibers of this map are going to be vector spaces of some constant dimension. So you can think of this as a family of vector spaces that varies as you vary the point on X. Okay, so what's a section of this? Okay, so the definition of a section of V, so let me just underline this, that's what we're defining. It also is a function. It's a function S on X, but where do the values take place? The values take place inside this vector bundle V. So they're inside this V. And they have to satisfy a certain property. It's the following one here. The composite PS equals the identity on X. So S goes from X to V, and then P takes you back from V to X. So this composite is a map from X to X, and you want this to equal the identity on X. Okay, so this is a bit of a funny condition the first time you see it. So let's try to look at it pictorially. Okay, so we can consider our vector bundle and picture it like this. So here's V, and here's our X. And the map P here will be just something which is given like projection. Okay, that's how we should picture it. Okay, so let's consider S of X. So we pick some point X inside our base X, and S of X has to be inside V. It's somewhere here. So here's S of X. Okay, so what does this condition mean here? Okay, let's try to unravel this condition in terms of this picture. So you apply S first, so you go from X to this S of X, and then you apply P to it, so you project back down, you have to get the identity, so you have to get back to X. So projecting down from here lands you back inside X. So that means that it must have been in the fiber above X. So this line is P inverse X. This vector space associated to the point X, then S of X has to be a point of that. So S of X has to be in P inverse of X. So remember, this is a vector space. Okay, this is a vector space. So this section generalizes a vector valued function. X has to map into some vector space, the vector space corresponding to the point of X. But the thing that's a bit funny now is that this vector space will change as you change this point. So the values do lie in a vector space, but that vector space will move. Okay, so as you vary X, you can see the value of S of X will change. So maybe it'll be something like that. So S is a map from X to V, and maybe its image will look something like this. Okay, so that's how you should picture a section. Okay, so where does the name come from? So the way you should probably think about this is you should think of this as being like a cross section. You can see this image of S, and basically it cuts across. You've got one point for each of these fibers. So it cuts across all these fibers, so it's like a cross section in that sense, and hence the name a section of the vector bundle V here. Okay, so let's have a look at some examples of sections of vector bundles. And the first one that we're going to look at is the trivial bundle, because looking at that we'll see in fact exactly how sections do generalize functions. Okay, so remember when we look at vector bundles, we usually look at families of vector spaces over some field F, and the usual choices for F are either the reals or the complexes. So let's suppose we have a trivial F bundle. So what's that? So the bundle itself will be X cross some number of copies of F, the field, so say F to the R, and the map from this to X is going to be you just project onto the coordinate of X. So X comma V just goes to X. So this is the trivial F bundle. And let's see what it means to give a section. Okay, so firstly, it's a function which goes in the reverse direction from X to this vector bundle. So X to X cross FR. And of course, what does any function like this look like? Okay, so you pick a little x inside here, well, you have to give the coordinate, the first coordinate, so that's some function of this little x, so that's g of x, say, and then you have to give the second coordinate, and that's some function of this little x, say f of x. So that's the first thing you need, that's the data that's required to give a section, and it has to satisfy this axiom here as well. So PS has to equal the identity. So let's see what that condition means, and it's quite simple in this case. Okay, so let's apply S to this little x, so you get here, and then you apply this P, which means that you pick up this coordinate here. So that's g of x on the left-hand side when you apply it to x. G of x. And that should be the same as the identity applied to x, so that's just g of x equals x. So to be a section here just means that this function here has the form g of x is just the identity on x. So S maps x to x comma f of x. So what's the data that's involved to actually give something like this? The only thing you need is this function f of x, which goes from x to f to the r. That's all that's involved. And what's the set of all these x comma f of x's? Well, you can think of this as just a graph of f of x. So the set of all these points, it's like the image of the section, it's going to be a graph. So that's the most important upshot here, okay? So the data of a section, if you have a trivial vector bundle, is just a function from x to f to the r. And the exact correspondence, basically you view it in a different way because the section corresponds more to the graph of the function, okay? So in this case, the idea of sections of a vector bundle do actually generalize the notion of a vector valued function. Because if your vector bundle just happens to be the trivial bundle, then these correspond precisely just to vector valued functions. Okay, so let's look at a slightly different example. So this is one thing that I mentioned before. If you have a tangent bundle Tx, okay, what are the sections of them? So remember, the case of the tangent bundle, you have some smooth manifold X, and the fibers above each of those points are basically the tangent spaces. So what you need to give a section is to each point, you need to give a point in the fiber, so a point in the tangent space. And point in the tangent space is just a vector at that point. Okay, so a tangent vector at that point. So of course, here sections of the tangent bundle are just smooth or holomorphic vector fields, depending on whether you're looking in the category of smooth manifolds or the category of complex manifolds. Okay, great. So there's some good examples to keep in mind. And remember, what we want to do is we want to use these sections to alleviate the problem of paucity of functions in projective geometry. Okay, so let's have a look at maps to projective space. Okay, so how do we map into projective space? Okay, so let's just remind ourselves what projective space is. So we fix our field F, which will usually be the reals or the complexes, and look at the n-dimensional projective space, Pn. So basically, it's this set of homogeneous coordinates. Okay, so it'll be n plus 1 tuples, y0 up to yn. These are just scalars inside F. And we consider these only up to scalar. Okay, so we don't want we can't have all of them equal to 0, so we'll throw away the n plus 1 tuple, which consists just of zeros, and then all the others we'll consider only up to scalar. So in other words, we're just interested in the ratio between them, and hence this notation here. Okay, so you can think of these as homogeneous coordinates or as ratios. Okay, so what's the easiest way to map into this projective space? Okay, so we can do what we did before, and that's easy enough. Suppose we have scalar functions S0 up to Sn from x to f. Okay, so maybe x is some sort of a manifold. Then it's easy to give a map from x to Pn. Okay, you just send x to the homogeneous coordinate given by S0 of x is the 0th coordinate, S1 of x is the 2nd coordinate, and so forth up to Sn of x. Okay, easy enough. And this way we can get a map from x to Pn. Now remember, let's suppose we're in the category of complex manifolds though. And if this x is furthermore not just a complex manifold but compact, then the holomorphic functions to the complex numbers here are just the constants. Okay, so the only things that you'll get are constant maps. So that's not very interesting. That was the problem of paucity of functions. So how do we solve this? And I want to show you that sections of a vector bundle, and in fact a line bundle, which is just a rank 1 vector bundle, they're the things that are involved to solve this problem. Okay, so let's have a look at this map, and let's see whether we can try to get slightly more general objects which allow us to construct this map. Okay, so the first thing is that really we should think of these as ratios. Here, to make this work, we actually give actual numbers here, and that means this maps not just to Pn but also to affine n plus 1 space, n plus 1 dimensional affine space. That's too strong to require that, okay? It's too difficult to have that in general. So what the first thing you can do is, rather than mapping to actual numbers, you just need to know the ratios between these. So to know the ratios between these, you can replace this f with just a one-dimensional vector space. If you have a one-dimensional vector space, given vectors in that one-dimensional vector space, you can talk about the ratios between them. Okay, so that's the first thing. So still defines a map if these S0x up to Snx lie in a one-dimensional vector space. And that has the advantage then that here you're really just looking at ratios, okay? Because you're not identifying them with actual numbers in each of these coordinate slots, okay? They're just ratios. And the next part, which is the most important part, is that this one-dimensional vector space Vx, well, it can change as you vary x. It doesn't matter, right? This still makes perfect sense, right? If you change the x, you can make this n plus 1 values S0 of x up to Snx. They can live in a different one-dimensional vector space, but this still makes sense as a ratio, and hence as a homogeneous coordinates or a point inside Pn. So really, what do we have now? These S0 of x's, they all land inside this one-dimensional vector space. And this vector space can vary with your point x inside x. So essentially, this family of one-dimensional vector spaces, that gives you what? It gives you a line bundle. In other words, a rank 1 vector bundle. Okay, so that's the first interesting thing. And then what are all these S0 up to Sn? They're just sections of this rank 1 vector bundle. So if you have some sections of a rank 1 vector bundle, you can try to form a map like this. And the only thing that you have to check, of course, this is something that happens in the case here as well, is you have to make sure that you don't map to the case where all these coordinates are 0. So as long as the image of this lies where the coordinates are not all simultaneously 0, then you'll get a map to projective space. Now it's quite easy to visualize the map to projective space that you get using sections of line bundles. Okay, so let's have a look at a simple example here. X is some one-dimensional manifold, maybe like this circle here or something which looks a bit like that. And here we're going to look at the line bundle, which is the tangent bundle, so Tx. And so sections correspond to vector fields. So suppose you have a vector field like S0, which is given by the purple. So there's a tangent vector at each point of this x, and an orange vector field, so section S1 from x to tx, so it's given by these orange arrows. And so this is going to give you a map. So this gives you a map from x to P1. So what does each point get mapped to here? So if you're this one here, what you do is you look at the ratio of S0 to S1. So just the ratio of this vector to this one here. And of course, whatever that ratio is, it will correspond to a point of P1. And similarly for this one, this point here, you can look at the ratio of those two, or this one here. And the only thing that you have to check to make sure you do get a well-defined map to here is that you don't have both of these vectors being 0 at the same time. If they're both 0, of course, it doesn't correspond to a ratio or a point inside the projective line. Okay, so let's have a look at a much more precise example, and that's going to be called the anti-canonical embedding of P1, which is a very, very important object inside algebraic geometry. Okay, so we'll look over the complex numbers. We'll look at the projective line here, P1C, and remember there are lots of different ways of viewing it. The ones that we'll need are, firstly, you can think of this as the complex plane, C, with say variable Z, compactified with a 1 point at infinity. So it's a 1 point compactification of this complex plane. Of course, when you write it like this, you don't see the manifold structure at infinity. So if you want to see the manifold structure at infinity, you need to look at an open neighborhood of this. And an open neighborhood you can get by removing 0 from here, and that gives you Cz minus the 0, and you attach that to this infinity, and that turns out to be another copy of the affine line, or in other words, the complex projective plane. So the complex plane, rather. Okay. And if you want to study that, so here, this A1z, this affine line, corresponds to Cz. This affine line here is centered at infinity, so the coordinate that you should use is no longer z, it should be z inverse, which I'll call y. That will be useful for us later. So you can think of this projective line as the union of these two, but there's a big overlap here, unlike in this union here. Okay. So now what do we want to do? We're looking at the tangent bundle here to this P1, TP1. That's the vector bundle we're interested in, the holomorphic tangent bundle. So since P1 is one-dimensional, this will be a line bundle. It will be rank 1. Okay, all the tangent spaces will be one-dimensional. Okay, and let's have a look and see what all the tangent spaces look like. Okay, so let's suppose you're on this patch here, this A1Z. What do all these fibers look like? Okay, so it's one-dimensional, so I just need to give you a basis vector. And the way I want to think about tangent vectors is, given a tangent vector, you look at the directional derivative in that, given by that vector. So you just have to say what is differentiation. And so d dz, of course, is well defined on all of A1z. You can differentiate on all of the complex numbers here. And so that gives you your basis vector. What we'll also need is we'll need to convert this over to the y coordinate as well. So let's do that, okay? So of course that's a simple change of variables, easy enough. d dz is the same as dy dz times d dy. So what's dy dz? So y is just the inverse of z, okay? So when you differentiate y, you just get minus z to the minus 2, and then you have d dy. And let's write this all in terms of y. So y was z inverse, so this is just negative y squared. Okay, so that's our change of variables formula when you slide from this patch over to this patch. d dz becomes minus y squared d dy. Okay, so now what do we need to do? We need to give some sections of this vector bundle here, this line bundle. And I'm going to give you 3 of them, okay? S0, S1, and S2. Okay, so what's the first one? The first one is S0 equals d dz, okay? So of course this is all well defined above here, okay? You just give that the basis vector, which I defined, that I gave you, so that's what it is there. But you also have to say what happens at infinity, at this point infinity here. you change coordinates to the y coordinates. So let's write this over in the y coordinates. So d dz, of course, is minus y squared d dy. And when z equals infinity, that's where y equals 0. So basically at infinity, it'll just be 0 times this basis vector for the tangent space at infinity. Okay, so it's just the 0 vector, in fact, inside there. Okay, so we found that this d dz, it is a vector field on all of the complex plane, and it also extends to a vector field over at infinity as well. So it is a holomorphic vector field on the whole of the projective line, in fact. Okay, so there are actually more, so let's do another one. I'm just going to multiply this d dz by z. So whatever value of z you have, whether it's 4, 5, or whatever, you can multiply this basis vector for this one-dimensional tangent space by that value, and that's going to be the section. Okay, that's the value of the section. So it's z times d to z. Of course, you have to make sure that it's well defined at infinity too. So what do you need to do? You need to work out what is its value, what it should be at infinity. Well, you just multiply this by z, and z is y inverse, so you multiply this by y inverse. And of course, your answer is just minus y times d dy. So it's still well defined here, okay? In fact, it's the 0 vector inside here, because this d dy is going to be a basis for the tangent space at infinity. Okay, let's keep going. We can multiply this one here also by z, so it's z squared times the original, and that means that you multiply this over here by y inverse, and you get minus d dy. So here you just get minus 1 times the standard basis vector that I chose, okay, that chosen one. Okay, so that's rather interesting. You get 3 different holomorphic sections of the tangent bundle to the projective line. You may think, can I go further? Let's multiply this again by z. If you did that, you multiply this by y inverse. And remember, you're looking at infinity, means y equals 0. So you're dividing by 0, so it's not defined. So it turns out that when you get to here, you actually have to stop, okay, if you try to use this trick to create more holomorphic sections. And in fact, it turns out that these 3 holomorphic sections, this spans the space of all global sections of this line bundle. So the only other way you can get other sections is to take linear combinations of these, in fact. Okay, so we've got 3 sections. So what does that allow us to do? We can form a map from P1 using S0, S1, S2. You just look at the ratio of these 3 and map it over to P2. And let's suppose our P2 have homogeneous coordinates u, v, and w. Okay, so let's see how that goes. So where does a point z go to? Okay, so S0 of z is just given by this basis vector d dz. S1 of z is z times d dz. And S2 of z is z squared d to z. What's the ratio between these 3? So you look on this side when z is not infinity, and the ratio is simple enough, okay, because d to z is a common basis vector here. It's just 1 to z squared. 1 to z squared. And that's how you can map, at least on this affine patch, A1z, over to P2, 1z squared. Okay, but what happens at infinity? Okay, what happens at infinity is, well, you can try to do this over here and see what it should be. Well, this is a ratio, remember? So what you might want to do is say, well, I can divide by z squared throughout all of this, and it should be the same. If you divide by z squared, and as z goes to infinity, of course, these 2 terms will go to 0, so it should map to 0, 0, 1. So that's what it ought to be, but of course that's not rigorous, okay? And the key point is that using sections of line bundle, you can make this rigorous. Because what is this ratio? So now you have to look at the tangent space at the point of infinity, so where y equals 0. So you look here now, and you look and see what's the ratio between these vectors when you put in y equals 0. So when you put in y equals 0 here, you get the 0 vector. in the tangent space at infinity. Here you get the 0 vector as well, but here you get -1. So the point it gets into is essentially infinity gets into 0, 0, -1, and you can scale that by -1, which means that it's the same as 0, 0, 1. Okay, so it's rather interesting in this case. You might want to try to map to P2 using this formula here. But normally, if you just use this formula here, there's some funny business at infinity. You have to work out what happens. And when you use the theory of sections of a line bundle, you can make that completely precise. Because now these values, when z goes off to infinity, if you just leave these as functions, just holomorphic functions, they shoot off to infinity, so it's not defined there. But if you think of them not as holomorphic functions, but rather as sections of a line bundle, they don't shoot off to infinity. That's what the line bundle kind of does for it. Instead of shooting off to infinity, we find that here it goes to the 0, S0, z goes to 0, this goes to 0, and that goes to, well, -1 times this basis vector here. Okay, so that's wonderful. We have now constructed a map from P1 to P2. And you might think, oh, that's rather interesting. You can have a map from the projective line to the projective plane. And what is that map? Okay, so let's try to look at what the image of that map is. And that's also extremely interesting, in fact. Okay, so let's look at this patch where the first coordinate is non-zero. So you can replace it with 1. And what's the image here? The image is going to be 1 z squared. So which homogeneous coordinates u, v, and w can you hit like this? Well, the first thing to note is that, well, there's a certain relationship between the u, v, and w here. If you square the v term, that's this z, that's z squared, you get this term times that term. You get z squared. So you lie inside the locus where u, w equals v squared. So this is a homogeneous quadratic equation, and that defines a conic inside P2. And in fact, it's very easy to see that, in fact, the image of this map here is this conic inside P2. And furthermore, not only is this map a surjection onto this conic, but it's injective as well. So you have an isomorphism of the projective line with the conic inside P2, and it's given by these 3 sections of this tangent bundle. Now, if you've seen my playlist on projective geometry, you would have seen that non-degenerate conics inside the projective plane are all isomorphic to the projective line. And what's interesting in this case here is that we can construct the map from P1 to P2, giving that isomorphism in a very interesting way, using holomorphic sections of the tangent bundle in this case. But in general, you can try to do the same trick with other line bundles. Now, this is actually an example of very, very general approach in algebraic geometry. If you want to study some sort of compact complex manifold or some projective variety, you have this problem of paucity of functions. Okay. Now, if you want to study it, the best thing to do is to try to embed it into some space that you know well, like some big projective space. But how do you do that? Well, the way you do that is you look for sections of line bundles, just like we've done here. And the key question is, well, which line bundles are good ones to use? Well, if you can get ones which are canonically associated to that projective variety X, then you get canonical maps to a certain extent. And the canonical choices to use are the tangent bundle. If it's one-dimensional, that will be a rank 1 vector bundle, so a line bundle, or its dual. And if you have high-dimensional varieties, then you can look at what's called the highest exterior power of that tangent bundle, or its dual, to get a line bundle. So this gives you some of the reasons why it's very important to look at holomorphic sections of line bundles in algebraic geometry. And this solves the problem of the paucity of functions in projective geometry. I hope you enjoyed this adventure in pure mathematics.